Well, welcome back to the second talk this afternoon session. And the speaker is Professor Daniel Kirschen of the University of Manchester, who is again a genuine engineer, artist engineer, who has done a lot of work on the mathematics of optimization of systems and the related questions of stability, security, and so on. Daniel.
Thank you very much. Following Janusz has already talked about a number of things I talked about, so I'll be able to go fairly fast on those. Before I go into the topic, I need to give credit to the Pegasus FP7 project, which has inspired the latter part of this talk. So outline, give a bit of background. As I said, I can probably go quite fast on that because Janusz has done it. Then we have mentioned the power flow problem a number of times in previous sessions, so I'll give you a bit more explanation on that because I need that to go into what's called the optimal power flow problem, and then the security constrained optimal power flow problem, and then the worst case problem, which we haven't found a way of quite finding initials that go with OPF there. Maybe WC OPF or something like that. What is a power system? Well, we have the generators, we have the loads, and we want to send power from the generators to the loads, but it has to go through a transmission network, and the colors are not working quite right, I'm afraid. And really what I want to talk about is how do we make sure we don't get into trouble in a transmission network, essentially avoiding the blackouts that Janusz talked about. This is dreadful. It's looking all right on my computer, it's looking terrible on this one. Yeah, not much better. Sorry. Janusz talks very politely about what running a power system is about as being a question of cost-benefit analysis. I'm a bit more brutal than that. I say on the one hand you have greed, on the other hand you have fear. Greed because it costs a lot of money or there's an opportunity for big profits. Fear if you're the system operator, if there's a blackout. Well, the usual question is when does a blackout occur? And the best answer I've ever heard on that one was from somebody who was responsible for operating a power system, and he tells me in the last 8 hours of an engineer's career. So that's very profound because it really summarizes the attitude of power system operator to all these security issues. Their jobs is on the line, their health is on the line. They take it very, very seriously. Now, those are the two traditional dimensions. In recent years, we have added, should also be green, in the sense that we have to accommodate renewables. So we spend years and years balancing the fear and the greed. Now we have to add the environmental impact. And my view of power system and the problem is, where do we sit in this triangle between cost, reliability, and environmental impact? How do we satisfy all these three things at the same time? So that's a very big background. Let me talk a bit about the power flow problem. The state variables in our problem are the voltage at every node, or as we like to call them, every bus in the network. And because we are dealing with AC voltages, AC networks, voltages are represented and currents are represented by phasors, which are essentially complex numbers in polar representation. So we have as state variables the voltage magnitude at each node and the voltage angle at each node, Vk and theta k. Now we have a bunch of other variables. We have the active and the reactive power consumed at each bus. In other words, the load at each bus. P is the active power, Q is the reactive power with a superscript L. We have the active and reactive power generator, which should be PGK and QGK, which I forgot to mention here. And then we have the active and reactive power produced by the renewable generators, PWK and QWK, where W stands for wind. When we treat the problem as deterministic, we assume those are known. In practice, they are stochastic variables. Now, what is reactive power? Because we keep talking about it, nobody has bothered explaining what it is. I can hear my power engineering colleagues wondering, how is he going to get out of that one? Because it's well known that it takes us years to get that through electrical engineers what the meaning of reactive power is. And then I thought, this is worse because I'm talking to mathematicians, and mathematicians like rigor. How am I going to do this with rigor and not use the whole time allotted to me to do it properly? Then I remembered something else that mathematicians like. Beer. Anticipating a bit, 5 o'clock. And I'm going to use an analogy. The active power is that part of the beer. The reactive power is the foam at the top of the beer. It's not really beer, but you don't get a good pint without a bit of foam at the top. Okay? At least for lager, I'm Belgian. That's the only kind of real beer there is. So, that's my explanation for reactive power. If you're not satisfied with that, see me after the lecture. I'll give you the 10-minute explanation that I gave to Danny last night, and he seemed reasonably happy with how I explained it. You buy me the beer, I'll give you the explanation. So, next concept I want to introduce is a concept of injection. So let's consider one of these buses. That's the way we represent them in our networks, or network diagrams. So essentially nodes in the networks. And at this node, I have connected a conventional generator, some kind of wind generation, and some kind of load. And I'm going to call the injection at this bus the sum of, well, the active injection will be the sum of PGK, PWK, and minus the load. So that's the active power going from these things connected to the bus into the bus, and from there on into transmission lines. And I also have a reactive injection QK, which is QGK plus QWK minus QLK. Now I've shown here the generic bus that has everything. Typically you have only one P or Q component at each bus, meaning only one type of generator, but you always have a P injection and a Q injection at each bus. So at the bus I have voltage, magnitude, and angle, and I have the active and reactive injections. And at each bus, you specify two of these four variables. If you are dealing with a load bus, a bus where you only have a load, you specify PK and QK. If you have a generator bus, you specify PK and VK. And there's one bus in the system where you specify VK and theta K because you need to measure the angle with respect to one thing. Now, that bus, I have the injections, but I also have lines going from bus K to other buses. If I call PKJ and QKJ the active and reactive power flowing from bus K to bus J. And the amount of power that flows from along this line here is going to depend on the voltage magnitudes and angles at both ends of these lines, and as well on the network parameters, GKI and BKI, which are the real and imaginary part of the network admittance matrix I hope you'll spare me the time from explaining that. And the power flow essentially is just a coupled power balance equations. At each bus in the system, I write the balance for the active power and the balance for the reactive power. Essentially, I say that the active power that is injected at the bus cannot stay in the bus, it has to go somewhere else. It flows to the other buses, and what flows to the other bus is given by this expression, and then you do the same thing with the reactive power. And you have these two equations for each node or each bus in your network. We have used that theta Ki is a difference in voltage angle between bus K and bus I. So, the power flow problem is the basic power system problem. If I give you the injections and the generator voltages, you solve the power flow equation to find the voltage magnitudes and the voltage angles at each bus in the network, and from there you get the flow in each branch. And that's what those equations look like. They are nonlinear. That's one problem. The other problem, as I just mentioned, N is 1500 for the GB transmission network. If you're looking at the continental European network, the model we're dealing with these days is about 13,000 nodes. So we're talking about 26,000 equations. Highly sparse equations, because typically each bus has only a bit more than 2 neighbors. So it can be solved quite easily. By the way, if anybody here is in sparsity, anybody working in sparse systems? Sparsity was invented by a power system engineer, by the way, just for that reason. So, why do we use the power flow problem? Well, we want to check the state of the network. We postulate a set of conditions, or we look at the current state of the system, and we calculate the line flows. We check whether all line flows are within limits. We check that all the voltage magnitudes are within limit, meaning we don't want to get the line sags that Janusz mentions, or we don't want the voltage to start collapsing, or don't want the voltage to get too high and get insulation problems. We can also do that by removing some of the lines to see what happens when you have to disconnect the line to let a cruise ship go out to sea. There are other reasons why we disconnect lines in power systems. Ben mentioned yesterday what he called the DC power flow, which is essentially a linear approximation to these equations. So essentially you take these equations, you assume the voltages are constant equal to the nominal value, you ignore the reactive power, so you use flat Beer. And that's very nice because it's linear, but it only works, it's only useful when you're only interested in line flows. If you're interested in the voltage magnitudes because you're worried about voltage collapse problems, this is no good. Right, that's a power flow problem dispatched with. Let's talk about optimal power flow. And there I need to talk about the type of control variables. Essentially, we have 2 types of control variables in power systems. Those that have a cost and those that don't. And the variables that have a cost correspond to essentially the amount of active power that a conventional thermal generating plant produce. Because the more power you put in, the more fuel you need to put in, the more money you have to pay. So if I change PK for a coal plant, that costs me money. If I change the voltage magnitude produced by that coal plant, it's just turning a knob, costs me virtually nothing. if I change a position of a device called a transformer, that position of a transformer, that costs me essentially nothing. So I have costly variables and non-cost variables to deal with. So that's the control variables. What can we try to optimize? Well, the standard problem, we try to minimize the cost of producing power with these conventional generating units. So it's a cost function of the amount of power that that generator is produced, summed over all the generators I have in my network. These cost functions typically taken to be quadratic or piecewise linear. It's a good enough approximation considering the quality of the data we have. That's one possible objective function. Sometimes, particularly if you're dealing with an electricity market, you're not really interested in minimizing the cost. The cost is not your problem. Maybe you're the system operator. What you have to do is make some adjustment to what the market would like to do just to maintain the security and stability of the system. But to make those adjustments, you have to increase some generations and decrease others. And that usually comes out of your system operator pocket, so you want to minimize the cost of those deviations. So essentially, you want to minimize the cost of the increase of some of those generators minus what you save by decreasing the output of other generators. And because market traders don't like complicated things, this tends to be linear. They can't handle quadratic stuff. Okay, what type of constraints do we have in this optimization problem? Well, we first start by the equality constraints, which are essentially the power balance at each bus. Our system has to be stable. So essentially, our system has to obey the power flow equations. So the power flow equations are the equality constraints in our optimization problem. And then we have the inequality constraints. And then there's a whole lot of them there, because we have to look at the upper limit on the power flowing through each line. We cannot overline, or not just lines, but also transformer, every branch in your network. We cannot overload those branches, otherwise we get big problems. We have upper and lower limit on the voltage at every node in the network. We have upper and lower limit on the control variables. For example, the active and the reactive power output of each of your generators. There are firm limits on that. The voltage settings of the generators and the position of the transformer taps and other control devices. So essentially, we are automating what a power engineer would do when looking at the results of a power flow. So if I want a compact formulation of this, this is a pretty standard optimization problem formulation. I'm minimizing over the control variables an objective function which is function of the state variables x naught and the control variables u naught, subject to some equality constraint and some inequality constraints. The reason for the subscript naught will be clear soon. Nothing extraordinary, but we're talking something fairly large, but sparse. Okay, let's move on to the security constraint OPF. And that's because bad things happen. Occasionally, the lightning strikes. When the lightning strikes a transmission line, it causes a fault. That line gets automatically disconnected to prevent it being damaged or preventing further stability problem. So because those things happen, and because we cannot tell the consumers of electricity that we'll have to wait until we repair the system to give you electricity. We have to be ready for those things to happen. So we get a bunch of sudden changes in the system. I mentioned the line being disconnected because of an insulation failure or lightning strike. Generator being disconnected. Janusz gave some examples of that. A transformer blowing up. Despite the best efforts of my colleague Zhang Dong Wang, those things do happen. And as I said, the system must keep on going. Now, we must be guaranteed the system must be kept on going, so that's why we have this infamous N-1 security criterion that we discussed at length before the break. So the security constraint OPF in words could be formulated as follows. How should the control variables be set so that you minimize the cost of running the system while ensuring that you can keep on operating in a stable manner in both the normal state and all these contingency states, where I call the contingency state a state where I have lost one of the components of my network. And mathematically, we can formulate this as follows. Objective function has not changed because most of the time I'm in a normal state. So really I only need to worry about the cost in the normal state. But now, instead of having one set of equality constraints corresponding to the power flow equations for the normal conditions, I have one set of equality constraints for each of the contingency states, for the normal state and all the contingency states. So 0 is the normal conditions, 1 to NC corresponds to the contingency conditions. Similarly, for the inequality constraints, I want those inequality constraints to be satisfied not just in the normal state, but also in all the contingency states so that I can keep on operating even after this line has been lost due to a lightning strike. And then I've added something here saying that the magnitude of the difference between the vector of control variables in the contingency state and in the normal state must be less than a certain amount. Now that's because in some cases I have a bit of leeway. After the lightning strikes and I lose a line, maybe one of the other lines gets overloaded, but it's not going to sag instantaneously. It's going to take a while for the temperature of the conductors to go up, for the line to start going down towards the tree. So I may have 10-15 minutes to do something, and over those 10-15 minutes I may have time to readjust the dispatch of my generators in such a way that I reduce the loading on those lines. So I don't have, there are limits to what I can do, but I can often do something. And being able to do something after the fact, after the contingency has occurred, can save a lot of money. So that leads me to making a distinction between what's called preventive security constraint OPF and corrective security constraint OPF. In the preventive security constraint OPF, I say, now I'm going to be very conservative. I'm not going to consider any corrective action after the contingency. Essentially, the operator can be asleep when the contingency happens, and the system will keep on going. So that simply means delta UK max is 0, meaning UK equals U0. I'm not allowed to change the control variables for the contingency cases. On the other hand, you have the corrective security constraint OPF, where I allow at least some corrective actions. That means at least for some of these contingencies, I allow some redispatching of generation. I think some of these things are possible, and I take advantage of them. Word about size. Now the SCOPF is NC plus 1 times larger than the normal OPF. Now if we apply, well, if you consider pan-European, the UC transmission system model, as I said, is 13,000 nodes, about 20,000 branches, about 2,000 generators. If we apply the N-1 security criterion, we have to consider the possible contingency of all those 20,000 branches and all those 2,000 generators. So the problem is 22,000 times larger than the basic OPF problem. But not all contingencies are critical, but which ones? And also, most contingencies are only going to affect a local region. For example, it's pretty clear that if you lose a line in the middle of Poland, it's unlikely to have a big effect on flows in Portugal. But how do we figure out what part of the network we need to consider when we do this optimization problem? Now, this is an area of very active research right now. You know, this is not an absurd problem. People are working on this, but the way they are tackling it is by looking at those issues. Yes.
Is there a reason that usual sensitivity analysis doesn't deal with this thing?
Right. If you use a linear approximation, right, the DCOPF as it's called, yeah, then great. And that works very nicely for line overloads. But a lot of the problems we have to do with voltage. And the voltage is related to reactive power, and that part of the equations is a lot more nonlinear than the part about the active power and the I go back to the full equations. Here. This is reasonably linear. This is quite nonlinear.
I think it also you have to solve that 22,000 times x dimensional problem to find all about multimodals. I think that you don't even know where to start because you can't.
Yep. Now, so far I've assumed that all the variables are continuous. Fortunately, some of them are discrete. Now, some of them are nicely discrete. Transformers and phase shifted taps, you know, there's about 10, 15 positions, so discretizing is not creating major issues. Capacitor and reactor banks provide reactive power, but they're either on or off. So that's already a bigger discrete variables, harder to handle. And then sometimes you want to be able to decide, am I going to start up that generating unit? Do I need to start up that generating unit to keep my system secure? Or can I get away with not starting that generating unit? Now, if you start a generating unit, it has a minimum stable generation. That means a certain amount of active power it has to produce. And also, if it's there, it's also keeping the voltage constant at that point. So that's another significant discrete variable. And then there's another problem in that, I talk about corrective security constraint OPF. We can look at that on a theoretical perspective and say, yes, if you move this and this and that after the contingency, you'll be fine. But remember, there's only about 15 minutes, and this is going to be done manually. So the system operator, sitting in his computer console, suddenly gets an alarm message saying, this thing has happened. First, he or she has to understand, the details of what happened, understand the consequence of what has happened, and then implement those corrective actions. So there is only time for a finite number of these corrective actions. So even though when you solve the whole problem, you could find a solution that involves 120 adjustment to control variables, but the operator may only have time to implement 3 or 4. And therefore, that may not be an acceptable solution. It may be a theoretical solution, but it's not an acceptable solution in that formulation of the problem. Okay? So, the security constraint OPF is because bad things happen. The worst case problem comes because good things happen. We want to have renewable generation, we are going to save the planet. Okay? But there's no free lunch. Somebody has to worry about it. And the problems come in because wind generation, solar generations, all those nice renewables, except tidal, can only be predicted with limited accuracy. So we don't really know how much wind generation I'm going to get in different parts of the country tomorrow. And typically planning is done a day ahead of time. So when I'm planning today for tomorrow, I don't know exactly how much wind there will be and how much wind there will be in different locations. So talking about stochastic variables. But as we said before, power system operators do not like probabilistic approaches. Now, very good explanation for that. Has to do with psychology. Remember, the system operator's first responsibility is to keep the lights on. If there's a blackout, they feel terribly guilty because if you have any large-scale blackouts, people die. It's a pretty clear connection there. And so they want to be able to say, I did what I was supposed to do. I did what the rule book said I had to do, so it's not my fault. If they have to start making judgments, is a 0.6 probability acceptable or not, we're in a gray area. They don't want to touch it. Okay? They want some very clear rule. They don't want to be in a probabilistic world. They want to be in a deterministic world. So, let's look at a formulation of the optimal power flow problem with uncertainty. I've modified a bit my objective function. I assume now that I am in a market-based operation and that the electricity market for tomorrow has decided the pattern of generation, how much each generator should produce based on the bidding. And as system operator, I'm allowed to deviate from that, but that will cost money. So I want to minimize the deviations between the market decision and what I really need to do, and that has a certain cost. Now, another thing I can do as system operator is to decide that the generators that are scheduled by the market are not sufficient. So I may decide to add commit some additional generators. And I have decision variables, binary decision variables for each additional generator, and a fixed cost, and then a cost proportional to how much each of these generators is going to produce. And I have my equality constraints, which are my powerful equations. I put a few more variables. I still have the state variables, but I have made a distinction between the non-cost control variables, the costly control variables, the decision variables about these additional generators, and how much these generators cost. And I have added this S variable here. It's a vector representing the uncertainties on the injections at various nodes in the network. That's what I don't know. You know, what is the wind going to do at various nodes in this network? And then I have my inequality constraints, function of the same variables. I have limits on what I can do on the control variables. I have limits of what I can do on the non-cost variables and the cost variables. I have limits of what I can do on this additional generators. And I assume that I know the range between which this unknowns range. Now, you will notice I did not include a probability distribution. Okay? I would like to, but part of this European project we are dealing with actual transmission operators. They don't want to hear about it.
Those values are huge.
I'm sorry?
If you really look at the min and max, it's going to be huge.
So I'm going to explain all of that. Now, that's the basic formulation. But really what they want to know is what is the worst pattern of uncertainty that could occur tomorrow. So we formulate this as a bilevel problem, where this is the problem I had on the previous slide. And I find the solution of that problem. And then I look for the pattern of uncertainty S that results in the largest cost. Essentially, I'm trying to find out how much could this uncertainty cost me. You know, do I really want to turn on that generating unit, that additional generating unit, to deal with this uncertainty out there? And here we are way beyond what we know how to solve this. We just formulated the problem. We don't know how to solve it. And in fact, we can go a bit further. That was the worst case OPF. There's also obviously the worst case security constraint OPF, where we do the same thing, considering that we are not only dealing with the uncertainty on the wind injection, but we're also considering the fact that we could have losing lines, losing generators in the system.
Could I just get a quick clarification?
Yes.
These may be details, so stop me and we'll talk later if they're just details. One is it looks like you have a linearity where the C transpose term looks sort of linear, where I might have expected it to be more like an absolute value or something.
You mean
in both the upper and lower levels, it almost looks like you have a linear term there where I would have expected an absolute value or like a deviation or something. But you know, the deviation of P0 from P0M would look slightly different to
you could save a bit of money occasionally by reducing people, but it's
okay, fine. But the other thing was that perhaps could you help me understand what's the difference between the objective of the lower level problem, the arg-min problem, and the upper level problem, the sort of max problem? Because if the objectives are sort of aligned, I don't know, maybe what is this? Tell me what this is again. This is the sort of a worst case.
Right. I'm trying to. Okay. Now I have this optimization problem. Okay. This one, right? Let's start with this one, right? I had this parameter S. Okay?
And
Let's
this is
suppose
like
I
a
know what it is.
Like a robust, this looks like a robust optimization. Is that a good description of it? Or?
Yeah.
Okay.
Right? Well, S, if I start by assuming I know what S, this is a standard security
Right.
constraint.
Now you say, what's the worst thing that could happen to me, sort of?
Yeah. And
Okay.
I'm trying to figure out what is the worst thing that could happen to me.
And so what, I guess, having solved the problem on the previous slide, why do I need this problem? I'm still missing the link. What's this one doing again?
Well, the problem in the previous slide is down here, right?
Well, but S is a variable in the previous slide.
Well, S a variable is in this one.
So what's the, that's the bit. So what's
This is the important one.
yeah, so what's the difference between the last slide and this slide? That's what I'm just,
Well, this one is a single level problem,
yeah.
and this one is a bi-level problem. So here I'm trying to find the S that makes my life worse. Okay. This one I was just saying, okay, let's assume I know S. I'm trying to minimize.
Oh, S isn't a variable here.
Yeah, exactly.
S is a parameter.
It's a
I feel.
parameter. Yes.
All right, so by the time you get to the second slide,
It becomes a
Is
variable.
it a max-min? Because max-min problems, at least, aren't necessarily this, they're not the worst bi-level problem. They're a sort of nice bi-level problem. Or is this a nasty bi-level problem?
I don't know. That's why
Okay.
that's why I came here to talk about this.
Okay, does anyone else have, because I would have guessed a max-min problem isn't necessarily, it could be a convex optimization problem. Whereas a bi-level problem can be much worse. But I may be barking up the wrong tree.
What if you do this AC? The DC probably, but AC is.
Oh, I see. Does it do with the nonlinearities as well? Speak up.
Discrete. Discrete as well.
Those as well.
If you
This
have,
discrete problem is
Yeah, you
just
got 0
minor
ones in
0
there.
1 variables. And how this G function is defined in terms of S? Is it linear relationship or non-linear relationship?
Non-linear.
Non-linear. So
Well, you can. Okay, if we could already solve the linear version of this, where we take the DC power flow, the linear approximation of this, that would be very nice. Ultimately, we'd like to solve the nonlinear version. That would.
this is
Yeah. I think that was my last slide. So.
we want more.
No, I'm just thinking if somebody has was hoping for good suggestions.
Where do you think the data for S is going to come from? You can't provide the data, there's no point to solve that.
In the back there, somebody doing that kind of thing for National Grid, I suppose, in some ways, or not yet. Yeah. Now, hopefully, there's a big data collection effort that's going to be needed to get some good ideas of what this uncertainty is about.
Good questions. Congratulations.
First of all, there's a big fashion in signal processing right now. To take these combinatorial problems and use L1 regularization to get L1 regularization. It's basically a convex relaxation.
Right.
And it can be brilliant how well it works in signal processing applications. And it's sort of a relax, instead of saying B zeros and 0, 1, you say it's general, but then you put an L1 penalty on it. And again, in signal processing, it's an amazing application. And here, maybe there's some hope of applying this in
Mm-hmm.
And the other thing is that I was in Caltech about a month ago, and a student, Stephen Lowe, had this amazing proof that even though that's a non-convex constraint, he looked at the dual and showed there was no duality here. I mean, it's an amazing paper. He used some very clever tricks to show there was no duality here. And so here, maybe the combination of tricks, you might be able to actually look at the dual of that and then knock out everything at once, because then the dual would give you the sensitivity issues as well.
Mhm.
I don't know. So there are two tricks that might be useful.
Okay.
Could you possibly describe the dual trick a little bit more for us? Or do we have to read his paper to understand?
I mean, it had this horrible, I mean, of course there was some, but I think he did have a linear objective and the same non-convex constraint.
But not non-convex due
The
to
AC,
binary variables? Or
No, the AC.
Oh, okay, the nonlinearities.
The nonlinearity, the quadratic. So you take the dual, and you can look at the dual nonlinear program, which is always a convex program. The problem is that when you start with a non-convex optimization problem, you typically have a duality gap. So the dual doesn't tell you much. But what the steps were ingenious to prove that there was actually no duality gap. The dual was actually convex, and there's no duality gap. So it solves the problem. And the proof of that is what? Easy proven for previous theory at one point. Just some very subtle grad students.
So what is the problem that the student looks at?
So basically, a version of this, which is a horrible non-convex nonlinear program. You took the dual, which is a convex program, and proved that there's no duality gap. Or specifically the AC optimal version of the AC optimal problem. And that's what's so hard. It's really no duality gap. I just got the paper from last week. But he showed me the proof. It's really fun. Anyway, it might be.
Does that also prove that there are no local optimizers?
No, it doesn't prove that. Because you can have a problem like this, horribly, lots of local minima, and the dual function will do look like convex and just puts it there.
So you can calculate the global minimum without calculating the optimal solution.
But you get the optimal solution.
From the multipliers and
You can reconstruct it.
so even though you got lots of local minima,
It'll
you
pick
can
out.
pick the right one.
So the signal processing work you're talking about is compressive.
Compressive sensing,
But there's some sparsity assumption built in
Well,
there. So
in
what's the
signal
connection?
processing, there's the sparsity assumption, but the idea of compressive sensing, the fundamental idea is just that optimizers are typically achieved at corners. So if you can put corners in the right place in your convex relaxation, then you can potentially solve it. So if you have like a startup constraint, you want to make sure the cost function has a sharp corner that lower limit of power generation. But it's just, I have no idea what to do.
It's worth trying.
It's worth trying. Further questions?
Can I ask you a very silly question? What is when you solve this problem and you solve it for S? What actually does that help? How does that help you?
The system operator can sleep at night.
What is it? So, what does it actually tell you?
Well, it reassures you that tomorrow, if you get the worst possible condition in terms of pattern of winds, and you get the critical contingency, you'll still be able to get through. Or you'll find out if you really need to turn on that additional generating unit that costs you an arm and a leg.
And there might be a sort of worry that this worst possible condition isn't a very well defined thing, and that this is transferred problems and worrying about the tails of some of the accessible.
Yeah, I'm not very happy with this. Because it's a very crude way of doing things. I'd be much happier to do this in a proper probabilistic framework. I think we would have simpler solutions. But, okay, system operators are what they are.
Andreas.
Yeah, probably related question, where do you get your S min and S max from? I mean, if this is sort of limits on wind power production, there could be anything from 0 to very high, and I would think, I mean, what do you think you get a solution out of there that says anything but don't use any wind? That's the only thing, or what?
Presumably what you do is you set your S min and your S max probabilistically, and then you tell your control room or your planners or whoever what S min and S max are without ever mentioning the word probability.
I think that's the way to deal with the politics of the situation, yes.
So your region of S being between S min and S max is a rectangle basically.
Yeah.
But if your random variables were Gaussian, you'd have ellipsoids that you are looking at, and if they are heavy tailed, you would be looking at only one of them being large typically, rather than all of them simultaneously being at their max or min values. Can you incorporate that?
I don't know.
Yeah, there's the I suppose there's the worst, there's the even worse than Daniel had dreamt of OPF, which
Go ahead.
which it's something I was talking about with people at the National Grid Control Centre last week, that the various forecast errors for your wind and demand and conventional plants, or the way in which the different forecast errors appear in the way they do things are correlated. So you get these sort of correlated errors in the different in the different forecasts involved.
Well, except I think this is worse. Mine is worse than yours. Because here those correlation could actually be good. Well, in this case, we're assuming the worst possible thing, which may be a meteorological impossibility.
Yeah.
If there is such a thing.
Yes. So you'll certainly. Yeah, you certainly won't underestimate. Yes.
A guy who was head of Operation National Grid a few years ago told me that he was paid to worry. That was his job.
I think the most important thing about probability is independence of events. Where's independence model here in this?
We don't want to hear about
We don't want to hear independence.
I agree entirely with you. It would be a lot nicer if we could do it nicely probabilistically.
So if I understand correctly, it becomes a separate problem how to pick the correct S's that sort of semi-correctly capture your actual probability distribution.
Ali?
A quick question: is it OPF is corrective action?
Yeah.
Not that PK minus P naught.
Yeah. Here we allow corrective actions. Here.
So and the base of corrective action was we have an outage, and after an outage we have, let's say, 50 minutes to take that action, and after that 50 minutes everything is within the, let's say, thermal ratings. I feel that we need another set of equations because we had the intact network, which is G naught and H naught, yeah?
Yeah.
And we have another GK and HK represent what? Represent the contingency
Contingency case, yeah.
which is within the emergency, immediately after outage, or after we take the action.
After you take the action. So this is kind of a
Because we need another
long term thing.
So we need to have a kind of set of constraint once the outage happens to make sure we still are within the limit of rating.
So I think that's taken care through this. Okay? Because you have the control act. This is a control action you can take. This includes the control actions you can take after the contingency. And so this gives you essentially the steady state equilibrium.
Okay, this is the steady state equilibrium after 15 minutes or exactly
after 15 minutes.
So in the moment of outage, we have to see if we have some overloads more than kind of emergency condition.
No, yeah, that's.
Is it right? Because we have three moments: the intact network,
Okay,
the moment of outage, and after the emergency.
Yes, you're right. But what they also say they want to do is do a dynamic simulation, time domain simulation, to see that you can actually survive long enough to reach that point.
Any further questions? Well, next meeting we're going to invite along some psychologists to tell us why power system engineers don't like probability theory. Whether there's anything you can do about it. Or another very, very interesting, stimulating, and quite provoking talk. Daniel, thanks very much indeed.